Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. In this lecture we will discuss one result for eigenvalues and eigenvectors. So let's start with this result or note. Suppose lambda is an eigenvalue of a square matrix capital A, and suppose x is an eigenvector corresponding to eigenvalue lambda, and suppose s is any real number, that is s is a scalar, then lambda minus s is an eigenvalue of this matrix A minus s into I, where this I is an identity matrix of the same size as capital A, and eigenvector of A minus s into I is exactly the eigenvector of capital A. So this remark says that if lambda is an eigenvalue of matrix capital A, then lambda minus s is an eigenvalue of matrix A minus s into I, and eigenvectors corresponding to eigenvalue lambda and lambda minus s are same. Eigenvectors do not change, only there is a change in the eigenvalues. So we will remember this result. If lambda is an eigenvalue of matrix A, then lambda minus s is an eigenvalue of matrix A minus s into I. If s is a negative real number, then we can say that if we want to find out eigenvalues of A plus s into I, then lambda plus s is an eigenvalue of matrix A plus s into I, where s is any real number. So if lambda is an eigenvalue of matrix capital A, then we can find out eigenvalues of A plus s into I by simply adding s to the eigenvalues of given matrix, and eigenvalues of A minus s into I can be obtained by subtracting s from the eigenvalues of given matrix. So we consider one example to understand this remark. So in this example we are asked to find out eigenvalues of these two matrices A minus 2i and A plus 3i for this matrix capital A. So as we discussed, if we want to find out eigenvalues of this type of matrices, then we don't have to find out what is this matrix. Instead we will find out eigenvalues of A, and if lambda is an eigenvalue of A, then lambda minus s is an eigenvalue of A minus s into I. So for this matrix capital A, first we find out its eigenvalues, and as we know, to find out eigenvalues of this matrix A, we find out the roots of the characteristic equation of this matrix capital A. So the characteristic equation of matrix A is determinant of A minus lambda I equal to 0, and this A minus lambda I is the matrix obtained by subtracting lambda from the diagonal. So we subtract lambda from the diagonal and we keep other entries as it is, so we obtain this determinant. Now we expand this determinant using first row. So with 5 minus lambda we have to consider determinant of this matrix 5 minus lambda into determinant of this 2 by 2 matrix, which is minus 1 minus lambda times minus 2 minus lambda minus 0 into minus 8, which is 0, then minus 6 times matrix of this determinant, so 0 into minus 2 minus lambda, which is 0, minus minus 8 into 1, so negative negative positive, plus 2 times matrix or determinant of this matrix, 2 times 0 minus minus 1 minus lambda, and equal to 0. Now we simplify this. Here we can take minus 1 common here also, so this is going to be 1 plus lambda into 2 plus lambda, this will be minus 48, and this we can rewrite as 2 times 1 plus lambda. Now in these two terms we can observe that 1 plus lambda is common factor. So if we take 1 plus lambda common, here we are left with 5 minus lambda into 2 plus lambda, and here we are left with 2, and we keep this minus 48 as it is. Now we simplify this bracket. So 5 times 2 plus lambda, which is 10 plus 5 lambda, minus lambda times 2 plus lambda, which is minus 2 lambda minus lambda square, and plus 2, minus 48 equal to 0. And this we can rewrite as 10 plus 2, which is 12, 5 lambda minus 2 lambda, which is 3 lambda, minus lambda square, minus 48 equal to 0. Now we multiply these two. 1 times 12 plus 3 lambda minus lambda square, plus 12 lambda plus 3 lambda square minus lambda cube, minus 48 equal to 0. So first we write down highest power of lambda, which is minus lambda cube. Then we collect the terms with lambda square, that is 3 lambda square minus lambda square, which is 2 lambda square, and then we collect terms which are with lambda. So 3 plus 12, that is 15 lambda, and constant term is 12 minus 48, which is minus 36 equal to 0. And then we multiply this whole equation with minus 1. So we have lambda cube minus 2 lambda square minus 15 lambda plus 36 equal to 0. So this is the characteristic equation of given matrix capital A. And if we observe that all the coefficients of this equation are integers, so this is a characteristic equation. Our left hand side is a polynomial with integer coefficients. Now as we know, if we have polynomial equation with integer coefficients, then the integer solution of this polynomial equation must be divisor of constant term, which is 36. So if there is any integer solution of this equation, then it must be a divisor of constant term 36. So we can try different divisors of 36, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, then 6, 9 is also divisor, 12 is also divisor, 18, and plus or minus 36. So by trial and error we can find out one integer solution by putting lambda equal to 1, lambda equal to minus 1 by trial and error. First we can check for lambda equal to plus or minus 1, then plus or minus 2, then plus or minus 3, and so on. So you can check, I have checked for these two do not satisfy this equation, and if you take lambda equal to 3, it will satisfy this equation. We can check by putting lambda equal to 3. For lambda equal to 3, this equation becomes 27 minus 2 into 9, which is 18, minus 15 into 3, which is 45, plus 36. Now this is 27 plus 36 is nothing but 63, and this is also 63. So we obtain 0. So this equation is satisfied for lambda equal to 3. So lambda equal to 3 is one solution of this equation. For the second solution we can use the method of synthetic division. Now because lambda equal to 3 is one solution of this equation, the one factor of left hand side is lambda minus 3. So lambda minus 3 is one factor of this left hand side, and this second factor we have obtained by synthetic division. So here we write down coefficients of lambda cube, lambda square, lambda, and constant term here. So we can see here coefficient of lambda cube is 1, then coefficient of lambda square is minus 2, then coefficient of lambda, which is minus 15, 36, and here we put 0, then we add these two, so 1 plus 0 is 1, which we multiply with 3. So it is 3, and 1 into 3, which is 3, which we put here. Then we add these two, minus 2 plus 3, which is 1. 1 is multiplied with 3, so we obtain 3, that we write here. And minus 15 plus 3 is minus 12. Minus 12 into 3 is minus 36, so here we obtain 0. So this is coefficient of lambda square, this is lambda, and this is constant term. So the another factor is lambda square plus lambda minus 12 equal to 0. Now this we can factorize by writing lambda equal to 4 lambda minus 3 lambda. So in the first two terms we take lambda common, so we have lambda plus 4. In these two terms we take minus 3 common, so minus 3 times lambda plus 4. And in these two terms lambda plus 4 is common, so we have lambda plus 4 into lambda minus 3 equal to 0. So we can see lambda equal to minus 4, 3 and 3. 3 is repeated eigenvalue, are eigenvalues of given matrix capital A. And you can see these 3 and minus 4 are divisors of the constant term. So if you put lambda equal to 4, this equation will be satisfied. So one solution we obtain, lambda equal to 3, we obtain by trial and error by putting divisors of the constant term 36. And after one solution is obtained, we can obtain other two solutions using this synthetic division. So we are able to find out eigenvalues of given matrix capital A. Now we are asked to find out eigenvalues of this matrix A minus 2 into I. So as we know, if lambda is an eigenvalue of matrix A and S is any scalar, then lambda minus S is an eigenvalue of A minus S into I. So if we compare A minus 2I with A minus S into I, we have S equal to 2. So eigenvalues of A minus 2I are lambda minus S, which is lambda minus 2. So we will subtract 2 from each eigenvalue of A to obtain eigenvalues of A minus 2I. So therefore lambda equal to minus 4 minus 2, 3 minus 2, comma 3 minus 2. That is minus 4 minus 2 is minus 6, 3 minus 2 is 1. So these are the eigenvalues of A minus 2I. We are also asked to find out eigenvalues of A plus 3I. So if we compare with A minus SI, S is minus 3. So eigenvalues of A plus 3I are nothing but lambda minus S, that is lambda minus 3, which is lambda plus 3. So eigenvalues of A plus 3I are obtained by adding 3 to the eigenvalues of matrix A. So we add 3 to each eigenvalue. So lambda equal to minus 4 plus 3, 3 plus 3, 3 plus 3, that is 3 minus 4 minus 1, 6 and 6 are eigenvalues of A plus 3I. So in this way we can find out eigenvalues of this type of matrices for any real number by simply subtracting this S from the eigenvalues of matrix A. So if we are asked to find out eigenvalues of this type of matrices, we will find out eigenvalues of capital A, and then the eigenvalues of this matrix are obtained by subtracting this scalar S from each eigenvalue of A. So this is all about today's session. I hope you like this lecture. Thank you very much.